And because we have a model that is based on actual data, more importantly, anytime we have a reasonable belief that the acceleration of our system is constant, we can use the model instead of using graphs to make the solution. The model was derived from the graphs. The graphs were a means to an end. So although I want you to be able to make graphs and interpret graphs, that's a tenet of the course, for this part, it was a means to get to a model that could be reused. So I want to explain to you a little bit about the model and how I'd like you to use the model to do things. And to do so, I'm going to start with the question that we just had. This is the runner question. And let's begin by I guess the best way I want to do this is to begin by saying, look, we have a group of variables. These are the motion variables. 4 of them are vector values. 2 of them are measured in meters per second. 1 of them is measured in meters. 1 is measured in meters per second, and 1 is measured in seconds. Now, I've tried to make this a bit of a journey where you guys were having to participate. But I said this about algebra earlier in the year, that some of you learned algebra but never understood algebra because you're given coping strategies that allowed you to solve problems without necessarily knowing what you were doing. Now, I don't think that's ideal, but I also have to give way to the fact that in public education, sometimes some kids are slower than others and may need some crutches in order to be able to move forward. So if you look closely here, you can sort the numbers given to you by just what their units are without knowing really what they are. If you are given a value that's in meters, it's gonna probably be the displacement. If you're given a value in meters per second, it's going to be the acceleration. The only time you have a bit of a concern is if you're given a value in meters per second. You have to decide then. Am I looking at the initial or the final velocity? And I know this sounds easy, but trust me, the whole goal of the problems I want to write is to try and obfuscate the obvious, to make you think about what's happening. So right now I'm being very deliberate and very obvious, and the problems that you have in front of you are those two. They are very deliberate and very obvious. That doesn't last much longer. It lasts just long enough for you to get the basics before we inch up the difficulty again. One of the things I do want to get that out of the way. Get out of the way. Get out of the way. Go away. There. One thing I do want to kind of focus on for a minute is this concept of initial and final velocity. Initial and final doesn't mean the very beginning and the very end. It's all based on a given time interval. But a problem can have multiple time intervals. It's supposed to be the interval upon which you are observing an event. Imagine a situation where you throw a ball upwards and the ball travels up to its highest point and then comes back down. Your event might be the entire trip of the ball, going all the way up to its highest point and back, or your event might be just following the ball to its highest point. Those are 2 different time intervals, and therefore would have 2 different initial and final velocities to consider. Your job is to understand the interval that you're observing, and note that sometimes a problem might have more than one interval. The problem that we did yesterday with the ball rolling up the ramp and then rolling back down the ramp further than it rolled up, right? The one that we did yesterday. Now, there's 2 intervals there. There's the interval up the ramp, because you had to find that displacement separate from the interval down the ramp so you could figure out how far the ball went. So breaking a problem up into intervals is something that you may have to do. The problem might not do it for you, and you have to understand what initial means. Where's the start of the interval you are observing? It's one of those things that you need to keep in mind. I know you're not writing any of this down because I'm looking at you not writing this down, but the initial velocity means the velocity at the start of your observable interval. Your note card's only going to say initial velocity, but you have to understand that it means more than that. Same with final velocity. Yeah. If I drop a ball and that's a hand, really is, and you're going to catch it, the ball is going to start with an initial velocity equal to 0, right? You dropped a ball, and somebody is going to catch it with an outstretched hand. A lot of people think the final velocity of the ball is 0. Well, you caught it, right? Final velocity for the interval we are observing. We are observing the interval of the ball falling from a height to just before it hits your hand. There's a separate interval that chronicles you stopping the ball. That's a different acceleration. There's the acceleration of gravity that pulled the ball downwards, and then there's the acceleration of your hand pushing on the ball to stop it. Every interval may have unique accelerations, and if the acceleration changes, that's the start of a new interval. Right? We only observe systems with one acceleration at a time, and those accelerations have to be constant. So the observable interval might feel obfuscated or cloudy. You have to define the interval. Now, let's take a look at this problem that we have in front of us. I'm going to get rid of all those for just a minute because I don't need them in front of me anymore. Oh, I guess I should write this down. Displacement. Make sure you remember that is x minus x naught. And acceleration. You can have the labels on your note card, that's fine. Now, I want to consider the problem that we have in front of us, the runner problem. The runner starts from rest, runs 100 meters, and does so in 10 seconds. We are assuming a uniform acceleration. There are 3 pieces of information given. You should be able to sort them out. And I don't have to think too hard about it. 100 meters has to be displacement. It's in meters. It's the only thing there that was given in meters. Initial velocity is given, but it's not stated as a numerical value, but they said starts from rest. Starts from rest means 0. Just like comes to rest will mean 0. And they say it takes 10 seconds. I've identified 3 pieces of information that have been given to me. Now, I'm confident I'm probably being asked to figure out the other 2. So I need a way to figure out the other 2. I have 2 models that can be brought to bear on this problem. Here's my first model. And here's my second model. One of these models is less suited to helping me than the other. Meaning, I don't know that I can use this model. Not right now. Because you'll notice there are 4 different variables in that model. And of the things I've been given, I can't use one of them in that model. Which means I can't solve for anything there. If I try, I don't know this one, and I don't know that one, but this is 10, and this is 0. There's no solution here. So when choosing the correct model, you have to choose a model that uses all of the 3 pieces of information that are given. And this model will work. I will be able to solve this model for something that is missing because I was given 3 pieces of information. So I'll do that. I'll say delta x equals 1/2 times 0 plus my unknown times 10. Oops, delta x is 100, so let me put the 100 in there. I don't usually put the units in an equation. Now, this can be solved for v, right? Not particularly hard, 20 meters per second. And now that I do have the velocity, I see a pathway that I could find the acceleration. Of course, I had to solve for the velocity first to do that, but that's not particularly bad. And now that I've done that, I can put 20 equals a times 10 plus 0. So a has got to be 2 meters per second per second. Not terrible? Well, what we had to do was solve for v in one function and use it in the other. Right, that's what we did. I want to point out to you that the whole idea of algebra is the capacity to do that one time for every instance and not have to do it again. I don't want my problems to constantly be two-step problems. I would like my problems to be one-step problems. And if I know that there's the potential, like in this question, to have to solve for something first before solving for something else, I could use algebra to make that happen. And I know I'm looking around the room and I'm seeing confusion. What I'm saying to you is that you solved for v first in this function and then plugged it into this function, right? Why don't we just do that one time and make a new function that does that for you every time? That's what algebra is supposed to do for you. Allow you to look at the arrangements of numbers and see how they work together. So we're going to do that. We're going to eliminate velocity between these two functions. Now, I am not convinced that you guys are particularly good at this. So I'm going to help you with this one. If you're in mechanics, no help from me. But this is AP1. I'm going to have a little bit of a softer hand. Where I have V, I'm going to put this. This is me using substitution to eliminate velocity between the two equations. I know that V actually can be represented as AT plus V naught. That's straight substitution. And just so you know, I did a different substitution in first period, so if you want to see it done differently, you can look at first period's video, because they're so fun to watch. They are not. They're terrible. Now, I don't want to leave it like this. I see the possibility that we can, collect terms that are the same, right? I have two V naughts in there. Do you see that? So I can get rid of those parentheses, and I can combine this and get AT plus 2 V naught. And I'm not happy with this either. I'm going to go ahead and distribute on both sides, because I can distribute the t and I can distribute the 1/2. So I'm going to do that next. I distributed the 1/2 first, and now I'm going to distribute the t. I now have a new relationship. You'll notice this relationship has 4 motion variables in it, but does not have final velocity in it. It's another to add to the list. Now, I need to make a couple of points here that are important to me. They may not be important to you, but it brings us full circle, and it's important that you see this full circle thing, all right? Just take this for a minute and consider us going to the side and remembering that delta x is x minus x naught. No. I'm just going to move the x naught to the other side. Not all of you are going to understand why I'm showing this to you, but a few of you should. Do you see it? I want you to see it. I desperately want you to see it. Because when we graphed velocity graphs, they were linear. And when we graphed position graphs, they were quadratic. This is the proof that it's not an exponential. It's a quadratic. We can prove it directly from what we did in class, directly from the data that we took. The data from area and the linear function, when combined together, prove that the position graph has to be quadratic, which means that objects that are falling under a constant acceleration obey a quadratic function for their position. And when we take data and the curve fit gives you A, it's actually giving you half of the acceleration. And when the curve fit gives you B, it's giving you the initial velocity. When the curve fit gives you C, it's giving you the initial position. All the things we talked about they're proven now, and we can count on them. Now, I don't want to go into this too much, but it's important to me that you see that that's there, that we can justify why our graphs are curved, and not only curved, but how they are curved, what function best represents them. Now, so take a moment, gather the information that's here, get it into your head, because I'm going to ask you to solve for the answers. And I'm going to go around, take a look at your work, and then pick on a few of you. So take a minute. I'm going to go back to the other screen. But it says the ball is thrown vertically upward, leaving the ground at 40 meters per second. There's an acceleration of 10 meters per second from gravity. How high does the ball go, and how long till the ball comes to rest? Pretty straightforward. Everybody got the basics? All right. I'll give you 2 minutes. Work it out. What I don't want to do is spend a lot of time showing you this, but I do need to spend at least 1 minute providing you with something that I think is of significant value. If you're trying to find a way to organize yourself, I'd like you to consider this organization. What I've done is I've just put the motion variables in order with all of the vector values going from position all the way to acceleration. So it's meters, meters per second, meters per second per second. These are all the vectors, and they're all together, and the time is on the bottom. There's 5 motion variables, but if you look, each one of these relationships has only 4 motion variables in it, which means for any of these, you're going to have to be given 3 pieces of information if you want to use one of these relationships, because they all have 4 pieces in them. And in an equation, you have to be given all but one thing to solve for that one missing thing. Does that make sense? If you look at the way I've put them on the board, I've displayed them in such a way that they are next to the variable that is missing. So delta x isn't here, and final velocity isn't here, and acceleration isn't here. The shrewd people in the room recognize that we got this relationship by eliminating final velocity, but it introduced acceleration into that equation. You realize that we could do that again. We could solve this for time, say, and then plug it in here to eliminate time, and create a new function that doesn't have time in it. Good algebra students should be able to do that. It's not a particularly useful activity for us, but if you consider yourself a good algebra student, you should do it. You should eliminate the variables by using substitution. I would work within these 2 functions because they're the easiest to work with because they don't have any squares or anything in them, and you can produce other functions. In a first period, I produced this function for the students, and I think it's important that you have it. I eliminated time by solving for time in the first equation and plugging it into the trapezoid equation and simplifying. In your class, we eliminated final velocity. So if you want to see it done, you can see it done. Obviously, there's one left. And again, I don't know that this is a specifically interesting activity to do, so I will not belabor it too much. But that represents all of Galileo's motion equations. These are the functions that go with uniform accelerated motion. And they're organized in such a way as to be next to the variable that is missing from them. I'm doing this because some of you need a crutch, and I'm going to help you with that crutch. I want you to read the 6th question, not the 6th one. Let's do the ball being thrown upwards. I think that's the 5th one. let me get you a crutch for just a minute. In the problem, we are asked how high the ball goes. First, you have to figure some things out here. The ball is thrown at a starting velocity of 40 meters per second. And we're told that the acceleration due to gravity is 10 meters per second. How high does the ball go? The maximum height reached by the ball. That's when the ball has a velocity of 0. Does everybody understand why that has to be true? If it still had velocity, then it's either still going up or still going down. If it's still going up, it hasn't reached its maximum height. If it's going down, it left its maximum height. Its maximum height is attained the moment it stops for that instant. Now, this should help lead you to how to get the problem, but there's one more step in here, and many of you didn't think to do this even though we've talked about it. So let's add a step in our notes. We've identified the information that's given. There's going to be 3 pieces, but these are all vector values. And because they're vector values, you have to make a choice. The ball was thrown upwards at 40 meters per second. Gravity is acting downwards at 10 meters per second squared. And the ball is going to come to some height like up there. The question is upwards positive or is downwards positive? You need to pick. It's an arbitrary choice, but one that has to be made and applied to the problem. Doesn't matter what choice we make, but we have to make a choice. So I'm going to ask you, do you want upwards to be positive or do you want downwards to be positive? If upward is positive, then now I go through and I have to be conscious and deliberate about selecting positive and negative for every vector value. So that means my initial velocity is expressly positive, not accidentally positive. I assigned it a positive value. And it also means my gravity has got to be negative. It's expressly negative because it's downwards. And we assigned upwards to positive. You need to choose the vector direction for each vector value. If you don't, your answers will be wrong. And you'll start taking square roots of negative numbers. Now, it doesn't work. Now, we need both of these. So you guys who struggle, this part I want you to think about. We don't have displacement. Now, if you're looking for displacement, you need a function that has displacement in it. Well, that's every other function except for the top one, correct? Now, if you want to know which function to use, be deliberate. I don't have time either. Since I want this and don't have time, you can select your equation by just carefully looking at what was given and identifying the one relationship that has got all the things that are associated with what was given and what you're trying to find. That's why I organized it like this. Put a question mark on the thing you're finding, and the other thing that's missing will lead you to the correct formula right away. Now, I don't want to give out crutches like this. I think you should be able to figure this out. But I also don't want to wait 20 minutes for you to sort through them all and figure out which one you can use. You got to pick the relationship that has the 3 things that are given and the one thing you're looking for. So 2 times negative 10 delta x equals 0 squared minus 40 squared. This should give me my value, right? Now 40 squared is 1600, I think. And then divided by 10 is 160, and divided by 2 is 80. So looks like delta x is positive 80 meters. The fact my answer is positive is important. Now that you have that, you can use any function that you want to figure out the other unknown, which is time. But I would encourage you to use given information when possible in case you screw up your math, which happens. So I'm going to intentionally use this one because it still has all the things in it that were given and allows me to use those things because I'm for sure got those right. Looks like it's going to be 4 seconds. If you done your math right, time comes out to be positive. All right? Not hard? I don't think this is tough. Let's find out. This one's what I would consider to be a testable question. Like if I was to give you a quiz first few minutes of class tomorrow, and aside from having to make the velocity and the position graph, this would be the problem I might give tomorrow. Student throws the ball downwards to a friend on the ground. It is 4 meters from the student to his friend below him, and he throws the ball at 20 meters per second. How fast is the ball going when the friend catches it, and how long was the ball in the air? Let's just remind ourselves that the acceleration of gravity is 10 meters per second per second. My expectation is that you're almost done. I want to come around and see your work, but you should be near completion. What did I say to do? Well, I said to start here. Put together a list of the things that you have been given. You can sort them by their units. 20 meters per second. It's got to be a velocity, and it's the velocity that he starts with. 4 meters. It's got to be displacement. It's in meters. 10 meters per second squared. You get no points in my estimation of writing these where they go, but I will probably allow you to be issued a point tomorrow by just doing that. Because in this room, I saw 6 or 7 people who couldn't do that. That's a problem. The ball starts here and is given an initial velocity of 20 meters per second downwards and is being caught somewhere below 4 meters away. And we're trying to figure out how much faster the ball is going when it reaches there. I'm drawing a picture like this because I'm being intentional about the next part, which is to indicate what direction is positive. I'm making downwards positive. The whole problem takes place going downwards. I see no reason not to make downwards positive, all right? Intentional. The ball traveled 4 meters downwards, was given an initial velocity that was downwards, and gravity is pulling it downwards. Intentionally assigning direction to make sure I've done it, so I don't get distracted. I don't need the problem anymore. I need relationships that can get me to the solution, and I'm going to start with this one. Do I have a relationship that has those 4 things in it? Of course I do. It's on the board behind me and should be in your notes, and on a note card tomorrow when you come to class. I'm going to use 2a delta x equals v squared minus v naught squared. It has all the things in it except for the one thing I'm looking for. So 2 times 10 times 4 equals v squared minus 20 squared. 2 times 10 times 4 is 80. 20 squared is 400. Add it to the other side, and I get v squared equals 480. of which I will have to take the root. Plus or minus the root, actually. And be careful. I want to show you something, but I'm going to run out of time. If the number inside here is negative, you made a mistake.
Excuse the absence. Again, it's an excuse. I'm sorry I don't see him. It's hard. Oh. Anyway, it's an excuse. I excuse the absence myself.
Okay.
And I forgot to give the other on a plane to go to New Jersey. I'm freaking out. I lost my kid.
Sorry.
You have her for him.
All right, I'll make sure he gets it into class.
Where is he?
I don't know.
There he is. Can I give it to him? I forgot
Sure.
to give him first period. I'm a mess. I'm telling you. I'm not feeling well. I'm so sorry.
No worries. No. You have to decide whether it's going to be positive or negative. The reason I bring this up is we intentionally set downwards as positive, but because this is a square root, you will have to decide whether to make this answer positive or negative. We're going to choose the positive answer because we said downwards is positive. I'm pretty sure the ball is moving downwards when it hits the person, or at least hits their hand. But anytime you take the square root, you must be intentional about the fact that a square root is always plus or minus. Mathematically, what that means is this equation, for some reason, can't give us the vector direction of the answer. That's what it means. Now, I'm afraid we would have finished, but you will have to do the rest of this problem on your own. I would probably have used this one. So because I'm recording, and I was fortunate enough to get that whole exchange recorded, great. I'm going to finish the problem. You guys are welcome to pack up because you, of course, have to go to class. I will point out that this might be a harder way to do the problem because it's a quadratic. And even though I said to you that you should always use the given information when possible, you're gonna have to use the quadratic formula here. That might not be easy for you, so you may wanna trust your answer and use something simpler. You can always try and trust your answer and do something simpler if necessary.